Math 2414, Partial Fractions, Video 10, Case 4, Three-Term Quadratic Factors. You might have been expecting Case 4 to be repeated quadratic factors, and although that is a case, I've decided to analyze this case instead. The reason is twofold. Number one, the extension from unique quadratic factors to repeated quadratic factors is essentially the same as the extension from unique linear factors to repeated linear factors, in the sense that if you have a repeated quadratic factor with a certain power, and whatever that power is, that's how many fractions you need for that factor in the partial fraction decomposition, where all of those fractions would have linear numerators instead of constant numerators. Second reason that I'm choosing this instead of repeated quadratic factors is when you solve for the unknown coefficients, the unknown numerators, with repeated quadratic factors, at a minimum, you're solving for 4 unknowns. Because if you have a repeated quadratic factor, it has to be there at least twice, and each fraction's numerator, being a linear numerator, would have a coefficient in front of x and a constant term. So at a minimum, you're solving for 4 unknowns or more, and without requiring everyone to use the same technology, or without a crash course in linear algebra, or for some people, a crash review in solving systems using matrices. I feel that the time invested in partial fractions with repeated quadratic factors would be too time-consuming for the amount of problems it would represent on the homework. By contrast, having a 3-term quadratic factor is not uncommon and is not that difficult to overcome. It may not be an intuitive approach, but it's not a difficult one either. And when I say 3-term quadratic factor, I mean something of the form ax squared plus bx plus c that's irreducible, meaning that it won't factor into the product of 2 linear factors, and additionally, b is not equal to 0. And actually, I should also say that c is not equal to 0. And of course, a is not equal to 0, because if it was, it wouldn't be quadratic. But none of the terms are missing. It has all 3 terms. This presents a problem when you're trying to integrate with respect to it, because with that middle term, we have to somehow account for it. And the way to account for it is to complete the square and use a substitution to rewrite the denominator in the form u squared plus a squared. Now, if you haven't completed the square in a while, I'll remind you how to do it. But I will point out that completing the square here is a little different than when solving a quadratic equation or balancing the equation of a circle to locate its center. In both of those cases, we have equations on which we can do balancing moves on both sides of the equal sign. But for something like x squared plus 2x plus 5, we don't really have an equation, we just have an expression. And so we have to balance our move for completing the square a little bit differently. First, I want to remind you how to complete the square. The idea behind completing the square is to take the quadratic and the linear terms, in other words, the terms with the x squared and the x, and figuring out what is the perfect constant to add to them so that the end result, it will factor into something squared. And it's really easy to figure that out, especially when the leading coefficient of x squared, when the coefficient of x squared is 1. All you have to do to figure out what number all you have to do to figure out what number completes the square is to focus on the linear coefficient, meaning the number in front of the x. And again, this is under the assumption that the coefficient of x squared is 1, which it is, and that's the only case we'll look at. If you want to figure out what to add to complete the square, you do 2 things to the number in front of the x. Take half of it, and then you square that product. Well, half of 2 is 1, and 1 squared is 1. So we need to add 1 to our expression. And add a 1. That's the number we want to complete the square. However, we have to keep this expression balanced, and to balance a plus 1, we use a minus 1. As a consequence, quadratic trinomial at the beginning now, x squared plus 2x plus 1, will not only factor, but it will factor into a perfect square. X squared plus 2x plus 1 factors into x plus 1 squared. And then we just gather up all the other terms. The plus 5 that was originally there, and the minus 1 we use to balance out the completing the square. Plus 5 minus 1, that's a plus 4. And if you'll notice, this expression now has the form u squared plus a squared. Not sure why I'm drawing an arrow. Let's try that again. So our denominator, if this weren't a denominator, would now have the correct form. And then we would move the calculus forward by doing a substitution. We would say let u equal x plus 1, and then we would play out the substitution from there. That would transform it into an integral where we can do an arctangent or a substitution dependent upon the numerator. Let's try one more with the x squared minus 6x plus 13. I invite you to try to complete the square before I do it. Feel free to pause the video. Remember, the premise behind completing the square is to find the perfect number to add to the x squared minus 6x so that it will factor into a perfect square. Now we still have our plus 13 lingering around. We'll do something with it in a minute. You know what number we're going to add? Well, we have to take the linear coefficient, take half of it, and square that result. Half of negative 6 is negative 3. Negative 3 squared is positive 9. We need a plus 9 here and balance it with the minus 9. I'll be honest, this isn't the end result that I wanted. So I'm going to go ahead and change this, and then I'll edit the problem to show you what I wanted to happen. This is going to be just like the previous one. Now, the new trinomial x squared minus 6x plus 9, one that we just created, is a perfect square trinomial, and as a consequence will factor into x minus 3 squared. Of course, plus 13 and minus 9 is plus 4. I didn't mean for a plus 4 to show up again. So I think I'll go to the next page and do one more just to show you that it's not always super convenient. But if we were here, we would let u equal x minus 3, and that would send us on our merry way. Let's try one more. Actually, I want to show you two more. One with what I intended on the previous problem, and I want to show you an example of what you would do if the leading coefficient of the quadratic was not 1. In other words, the number in front of x squared is not 1. But let's do this top one first. Notice it's still a negative 6, so when we complete the square, we're going to be doing the exact same moves we did in the previous problem. Move the plus 22 over. We're going to look at the negative 6. We're going to take half of that, and we're going to square it. And that's still going to be plus positive 9. Minus 9. Let's see, what will that give us? The new quadratic right here. That will still be x minus 3 squared. But the remaining pieces, plus 22 and minus 9, plus 13. And we would still do the same substitution, but when you get a number at the end that's not a perfect square, you have to think a little bit creatively. Because any positive number can be thought of as a perfect square, simply squaring the square root of something. So if we were doing a substitution on this, we would let u equal x minus 3, but in the context of the arctangent integral, or the formula whose the integral of u squared plus a squared equals arctangent, then we would let a little inconvenient, but it is a thing. But I did want to show you one more example of how to do this if your quadratic doesn't start with x squared. like in this second example where it starts with 2x squared. And if you're wondering why did I actually do this one in the denominator of a fraction, it's because I'm going to need that structure in order to fix the problem. The problem being there's a 2 in front of the x squared, and I don't want it in front of the x squared. How do you get rid of a 2 that's multiplied? Well, that's easy. You divide by 2, or equivalently multiply by 1/2. But the problem is, if I'm doing this in an expression, and not inside of the denominator of a fraction, the balancing move would be a 2, and then I would have a straight 2 where I don't want it. So I want to be able to balance this multiplying move, and if I'm inside of a fraction, I can simply balance it by putting it on the top. And being part of an integral, that 1/2 could be pulled out in front anyway. So we would have 1/2 of whatever the polynomial on the top was. Now the denominator, upon distributing the 1/2, would be x squared minus 3/2 x minus 1/2. And now we could play the complete the square game. So how would we play the complete the square game on this? Well, the exact same way we did before. We would leave a space for the number that we want. It'll always be plus because the last thing you do to find it is square something. Move over the number that's currently there, and then play the balancing game. And it's the fact that it's a fraction doesn't change anything. It's still the square of half of this. Well, 1/2 times negative 3/2 is negative 3/4. And negative 3/4 squared is positive 9/16. So we would need a, I'm going to make a subtle change here, folks. See that -1? Don't worry, everything's going to be pretty easy to repair. I think I'm going to make it a +7. So instead of -1/2, it's going to be +7. And there's a reason why I'm doing it. I'll explain why in a moment. But we still need to balance the plus 9/16 with the minus 9/16. And now the bottom, or at least the leading trinomial in the denominator, this one, will factor into a perfect square. And I'll admit that factoring with fractions involved is not the norm, but when you're completing the square, the factorization is predictable. I didn't mention this on the previous examples, but I'll go back and show you real quick. It's really easy, let's go back to the first one, to predict what number will appear inside of the factored trinomial. In other words, the perfect square. That +1, that -3, this -3. If you're completing the square, the thing that's in the parentheses is what you get while you're completing the square, but before you actually square. In other words, I'm focusing right here. It's what you get when you take half of the middle number. Half of +2 is +1. That's what was inside the parentheses. Half of -6 was -3. That's what was inside the parentheses. Half of -3/2 is -3/4. And that's the number that will be inside the parentheses when we factor. -3/4 squared. And then when we combine the other two fractions over here, the common denominator is 16, which means we would multiply 7/2 by 8 on both sides. On the top, we'd get 7 times 8, 56. And then we would subtract 9. 56 minus 9 is 47. And so our fraction over here would be 47/16. And on this one, if we were doing the substitutions, we would let u x minus 3/4. And think of the 47/16 as a squared. We would square root it and say a is the square root of 47/4. So as you can tell, some of these get really nauseating numbers involved. But going back to the first page for a second, because what you see on this page is as difficult as I'm going to assign. terms of completing the square. If you are doing a partial fraction decomposition and one of the factors in the denominator is an irreducible three-term quadratic factor, then you'll need to complete the square so that you can get it in the form u squared plus x